We're going to be looking today at reactions and why they occur. So the very simple way of explaining why reactions happen is that some elements want to lose electrons and other elements want to gain electrons, and this will make their valence shell full, and when they're full it's nice and stable so they don't react anymore. And that's not untrue, but it's just the very surface level understanding about why that happens. So we want to actually go a little bit deeper and look at, well, why is it that some might take electrons? Why might some give electrons? And why are other ones actually just sharing? So let's take a look at a couple of different elements. We'll start off with magnesium. So magnesium is going to have 12 protons. And we have neutrons in the nucleus as well. However, they don't really play a role in determining that reactivity, so we're not going to look at them right now. We're going to be focusing on our two big subatomic particles, protons, which are positive, and electrons, which are negative. And that simple charge that each of them have plays a big role in reactions. So for magnesium, we know that if it's going to have 12 protons, it's also going to have 12 electrons. And every single shell has to be full before a new one is added in. So each of these different energy levels or orbits or shells, each of these is going to represent a different place that the electrons can be found, but all the ones that are underneath are stable. So they've already been completed. They don't have, those electrons aren't going to be involved in the reacting themselves. So it's only the valence electron that really have any kind of impact on whether or not something's going to react. So here we have magnesium, and we're going to take a look at another one, which is fluorine, and this one has 9 protons. So we've got 9 electrons going along with it. So automatically, if I was going to ask you which one of these had a bigger atom, you'd probably easily say that it was magnesium. And the reason why you would say that is because here we only have 2 orbits, here we've got 3 orbits. So just the fact that we have another layer on it is going to make something larger. Just like if you happen to put on more clothes, you're going to actually get larger yourself because there's more layers to you. So we talk about this size going from the center of an atom to the valence electron as atomic radius. And when we're thinking about atomic radius, it is the basis upon which all of the other trends that we'll talk about occur. So atomic radius depends on 2 things, and these are in a specific order. First and foremost, it's going to depend on how many shells you have. So here we can see that the distance between the center, our nucleus, to that outside valence shell is going to be larger in magnesium than in fluorine. So the radius of that atom is going to be larger because it has more shells. So the first thing that matters is the number of shells. The shells are not the only thing that's going to matter, though. When we're looking at this, we're also talking about how we have some attraction that's going on. So here we have our positive center, and we also have all of these negatives that are going to be orbiting around that positive center. So that's going to have a play into how big or how small those different levels are going to be. Now, with our magnesium, we actually happen to have 12 protons, and this one has 9 protons. So obviously this one has a little bit more positive in the center, but it is automatically going to be larger because it just happens to have another shell. So let's look at something that's in the same period as fluorine. So let's take a look at lithium. Obviously, I cannot draw perfect circles, so this might have an impact on some of what we're looking at in the drawing, but the ideas will be there. So here we're looking at something that would otherwise be the same size because they both have 2 electron levels or energy levels. However, when we're looking at each one of these electrons that happen to be orbiting, we are thinking about what kind of force that we have between the positive center and those negative electrons. So hopefully you remember from grade 9 the idea that opposites attract. So here we've got 9 positives, but we don't have 1 proton and 1 electron. We have, for this single electron, we've got 9 positives that are pulling it towards itself. And here we only have 3 positives that are pulling the electron toward itself. So if here every single electron gets pulled in by 9 positives, and here every electron gets pulled in by only 3 positives, well, if we have more positives, that means that we're going to have a tighter, smaller atom. And so the second thing that matters a lot with atomic radius is going to be the number of protons. So if the number of shells is going to be equal, then our number of protons is going to determine what it is that is, how large the atom is. So let's just zoom down a little bit and take a look at what this would look like if we're looking at our periodic table. Every single time we go down, we happen to be adding on 1 shell. So the first row has 1 shell, the second period has 2 shells, and so on. So we're going to see that atomic radius increase downwards. So hopefully that makes a little bit more sense. The one that's a little bit trickier is when we're talking about the number of protons. So when we're looking in a period, we can notice that the one that we're going to have towards the front is always going to have fewer protons than the one that is further to the right, just because we happen to have more protons. So we're adding protons as we go. And so that means that the one that is going to be smallest is going to be the one that has the fewest protons in that period. So for that trend, we are going to see atomic radius increase this way. Okay? We'll come back to that in 1 second. So we've talked about atomic radius, we've talked about that idea of attraction, and attraction is something that we're going to keep on coming back to. So the first thing that we talk about when we're talking about attraction in atoms is that idea of opposites attracting. And this is what we call nuclear charge. So we've got a positive force in the center of the atom that is pulling the electrons in. There is a second thing that we can talk about that also has to do with how reactive an element is. And that goes down to the second rule of attraction, which is that idea of likes repel. Now we happen to have a whole lot of things that are negative that are moving around in this atom. So when we're talking about likes repel, we're just talking about our electrons. And this is something that we call shielding. So for every single electron that we have that's on the outside here, we've got some electrons that are inside that are actually repelling it. So this electron is going to be acted on by this electron, and this one's going to push this one away a little bit more. So anytime we have these different layers where they're complete, they're going to be pushing them away. And so we have that repulsion force, almost like layers of a shield protecting something on the inside. When we happen to have 2 things that have the same amount of energy levels, shielding doesn't matter, because for this electron, it has these 2 electrons in the inside that are protecting it, and for this electron, we still only have 2 electrons on the inside that are repelling or keeping things away. So even though we've added on more electrons to our valence shell, we're not adding anything on to the center, and it's only the layers that are inside that actually do the shielding or the repelling. So number one thing is we are always going to be looking at nuclear charge, and shielding has an impact on that nuclear charge, or the effective nuclear charge, because if we have more layers, we have more electrons that are going to be almost diluting that attraction from the positive nucleus, to the electrons. And so more layers equals the less attraction that we're going to have. So let's say that I happen to have lithium and fluorine here. I can ask myself, which one of these is it going to be harder to remove an electron from? So when we're talking about the amount of energy that I need to put into removing an electron, this is when we're talking about ionization energy. And then if we're looking at something where we have elements inside the same period, well, this is where we got to think about ionization energy a little bit more. So obviously this will take less energy to remove than the fluorine one, but when we have the same number of energy shells, then we go back to the number of protons. And because this happens to have more protons that are holding those electrons in place, one of these electrons is going to be a lot harder to remove than this one. Now remember, if I want to take away this electron, it's got 9 protons pulling on it. This one only has 3. So when we're thinking about ionization energy, we're thinking about the energy required to make something an ion. And something can become an ion either from losing or gaining electrons. But we're thinking specifically here about taking the electron away. So fluorine's going to have a very high ionization energy, while something like lithium is not going to be as high because it doesn't have as much attraction. If we're going to take a look at our periodic table and see how that translated, how that trend worked, then we would see that it would actually be, so fluorine and even lithium, both of these are going to have more attractive energy holding those in place because it has fewer shells. So lithium, it'll take more energy to remove this one than it will from one valence electron from magnesium, simply because it's further away, so it's easier to get. Hopefully nobody has any kind of relationships that are long distance, but one way of thinking about this is, if you happen to be in the same school as somebody, even though you're not as close as if you were in the same class as somebody, you're still seeing them every day, you still have that closeness, and so the attraction is stronger. However, if you happen to be dating somebody in a different province, then that distance is growing, and so you're not going to have as much of an attractive force, and it might be easier to lose that person. So here, since magnesium has more energy levels, and so it's further away, it's going to have a lower ionization energy than lithium. And we'll take a look at this by saying that, so when we're looking at ionization energy, it is going to be a lot easier to be able to remove an ion from things that are higher or lower down, so it's going to require less energy. Now you might notice that these are actually going in the opposite direction. So bigger atomic radius, the less energy it takes to remove something. If we're going across the period, again, those at the front of the period are going to have less positives that are attracting those electrons. So we're going to say the same thing here, where the ones at the front are going to take a lot less energy than the ones that are further back in order to attract those electrons or hold those electrons. So we're seeing that these are actually going in an opposite direction. Because fluorine has a much greater positive center than lithium is, it's going to actually have a greater electron affinity. So it has greater chance of being able to get an electron. And when we happen to add an electron to fluorine, it actually releases energy. So I think about it as in, if you happen to have an affinity for something, it means you really like something. Maybe you really like pizza, or maybe you really like ice cream. And before, when you're not complete, you're needing something to fill yourself up. You're going to go after those things that you have more of an affinity for. Once you have them, then you release the energy and you kind of relax. You're a little bit more stable. It's kind of like being hangry. However, if for something like this, for lithium, it's going to take a lot more energy for us to add it on there because there's not really a great attractive force that's pulling it in. So it's almost like we have to have extra energy in order to get lithium to take that electron. You can think about it as if something that you have a low affinity for, like maybe Brussels sprouts, where somebody it's going to take a lot of energy to be able to get you to eat that versus something you like pizza. So this still goes back to this idea of nuclear charge and shielding. If you happen to have a lot of different energy levels, it's going to take energy because there's just not much of an attractive force there. So the positive is not spreading out super far to be able to actually take an electron from somewhere else and add it. So it's going to have to be a forced process to make this take an electron. In the same way, here, when we're looking at these two, lithium and fluorine, because it's nice and tight and it's going to be smaller radius because of that attraction, then it's going to be easier for it to get an electron, and it actually releases energy, versus this needing to force energy, again, add energy to try and get lithium to take an electron because there's just not much holding it in place. So anytime we are looking at the metals, it's going to take energy to add an electron to a metal, and it's going to have release energy to add an electron to a non-metal, which is why we generally see metals being positive, not getting electrons but having them removed, and non-metals being negative because
and when we
of
happen
those
to add an
electrons being
electron,
added.
fluorine, it actually releases energy. So I think about it as
with electron affinity, if we're adding this to our chart
maybe
here,
you really like pizza, or maybe you really like ice cream. And
we might notice that
it
actually goes in the same direction as ionization energy. So electron affinity, the ones that are going to be over on this side of the periodic table, is going to have a much greater affinity for electrons, and the ones that happen to be toward the top will have a much greater affinity.
For something
Again,
like this,
relating to the idea
it's going
of
to take
attraction.
a lot more energy for us to add it on there.
So just
because there's not really
which
a
one,
great
based on the atomic
attractive
radius,
force that's
has
pulling it in.
enough attractive
almost
force
like
to
we have
actually
to
bring
have
those
extra
in,
energy
versus the ones
in
that
order
don't,
get
we have to kind of work hard
take that electron.
to force them to
Think
take
about it
it.
as if something that you have
The
a low
last trend that we're going to be
affinity
talking
for,
about
maybe
is
Brussels
something
sprouts,
called
where
electronegativity.
somebody has to, it's going to take a lot of energy to be able to get you to
So when
use
we're
that
talking about
versus
electronegativity,
something like pizza. So this still goes back to this
actually
idea
an
of
average
nuclear charge
of-
and shielding. If you happen to have
It's actually an average of our ionization
it's
energy
going to take
and our
energy
electron
because there's just
affinity.
not much of an
Ionization
attractive force
energy
there.
is looking
So
at
the
how much energy do I
positive
have to
is
put
not
in to
spreading
remove
out
an
super
electron
far
from
to be
you.
able to actually
And electron
take an
affinity
electron
is it's
from
almost
somewhere
like
else
how
and
much
add it.
energy is there
So
that
it's
you
going to
are
have
in
to
order
be
to pull that
a
electron to you.
process.
So if there's not a lot of energy there when it comes
In the same
to
way,
pulling that electron in,
here,
then we
when we're
have to
looking at
add
these
that
two,
energy ourselves.
lithium and
However, if
fluorine,
you're like fluorine and you do have
fluorine
that nice attractive
because
force,
it's nice and tight,
then you
and
actually
it's gonna be
release
smaller
energy
radius
rather than
because
having
of that
it added in.
attraction, then it's going to be easier for it to get an electron, and it actually releases energy, versus this needing to force energy, again, add energy to try and get lithium to take an electron because there's just not much holding it in place. So anytime we are looking at the metals, it's going to take energy to add an electron to a metal, and it's going to have release energy.
With
to add an
electronegativity,
electron
since it
to a
is this
non-metal,
balance,
which is
we
why
are looking
generally
at
see
the ability
metals being positive
of something to be
not
able to
getting
pull an
electrons, but having them
electron.
removed, and non-metals being negative because of those electrons being added.
And I want to just make sure that we
So with
have this
electron affinity,
understanding
we're
straight.
adding this to
When we are
our
looking at
chart.
electronegativity, we're looking at it within a bond, so between
We
two
might
elements.
notice that
And the best way to
it
think
actually
about this
goes
is a
in
tug
the
of war.
same direction
So if we happen to
as
have
ionization
one that is
energy.
stronger
So electron
than
affinity,
another
the
one,
ones that are going
then
to be
the
over
one
on
that's
this
stronger
side
is
of the periodic
always going to be
table
able to
is
win
gonna
those
have a much
electrons.
greater affinity
But
for
if we have
electrons,
things that are
and the
fairly
ones that
equally
happen to
matched,
be
then we don't
towards the
have a
top
clear winner. We
will
don't have
a
one
much
that
greater
specifically
affinity.
takes it
Again,
versus
relating to
another
the
one that's going
idea
to be
of
losing it.
attraction.
So anytime we're talking about
So just
electronegativity,
which one,
we're looking at
based
an
on the
average
atomic
of
rays, has
the amount of
enough
energy that it
attractive
takes
force
to remove
actually bring
something,
those in,
and also the
versus
amount
ones
of
that don't, we
energy
have to kind of work hard
that
to-
is to add an
force them to take
electron
it.
to there.
The last trend that we're going to be
So
talking
for
about is
electronegativity,
something
we're
called
going to see,
electronegativity.
since it is an average of both
So when we're
electron
talking about
affinity
electronegativity,
and ionization energy, it's going to follow the same pattern.
It's
So all you
actually
got to keep
an
in mind
average
really is that the one
of-
that is different is atomic radius.
It's actually an
Simply
average
because
of our
bigger
ionization
atomic
energy
radius, less
and our electron
energy is
affinity.
required to make that
Ionization
electron.
energy is looking at how much energy do I have to put in
When talking
remove
about
an electron from you?
electronegativity, so we're talking
And
about that kind of
electron
like
affinity
pull,
is
the
almost like
attraction.
how much
I'm
energy
thinking
is
about
there
it
that you
as
are
a
going to
tug
pull
of
that
war
electron to.
between two
So
elements.
there's not a lot of
We've got a
energy
couple
there
of different
when it
things
comes
that we can have
to
happen.
pulling that electron in, and we
So,
have to add that energy ourselves.
If we happen to have
However,
a
if
really
you're like
big
fluorine
atomic
and you do have
radius,
that nice attractive
and we're going to
force,
have
then you actually
low
release
ionization energy
rather than having
and
it
low electron affinity, then we're also going to have a low electronegativity, which means that it's probably not strong. It's not strong enough to actually be able to take electrons, so this is going to give up electrons. If we're in the other situation where we happen to have a really small atomic radius and we have a big ionization energy,
we are looking
that means
at
we're going to have
the
big
ability
electron affinity. That
of
means
something
that
to be able to
we happen to
pull an
have
electron.
that element has a lot of strength with its ability to be able to pull electrons away from others. So this
And
one's
I
going
want
to
to just
be
make
the
sure
one that takes
we have
electrons.
this understanding.
However,
when we
we can also
looking
have
at
a situation where it's not a
electronegativity,
give
we're
and
looking at
take.
it within a bond. So
This
between two
happens.
elements.
So this
And the
give
best
and
way to
take
think about
happens
this
when we
is
have
a
one that is
tug of war.
clearly
So if
stronger
we
than the
happen
other.
to have one
However,
that is stronger
we might have some
than
that are
another one,
almost
then
equally
the one that's
matched, or
stronger
one
is
might be
always gonna be
stronger
able to
but
win
not
the
strong enough to
electron.
take everything.
But if we have
In this
things that are
situation, the give and
fairly
take,
equally matched,
we're thinking about a
we don't
bully who's
have a
strong
clear
enough to
winner.
just
We
come
don't
and
have
steal your
one that
lunch.
specifically
In the
takes
other
it
situations, we're
versus
talking about a
another one
friend
that's
that you
going to
either split your lunch equally,
So anytime
or
we're
maybe
talking
they
about
happen to eat,
electronegativity, we're
3/4 of your lunch, but you
of
still get to
the
share
amount
it
of
because you're
energy
still
that it
having
takes to
that
remove
last quarter.
something, and also the amount of
So when we're
energy,
talking about electronegativity, there
that
is a range
to
here.
add an electron to there.
And if we happen to have an element
So
on
for
this side
electronegativity, we're going to see
and an element on this
there is
side,
an average of both electron
then what we
affinity
have in the
and
center
ionization energy.
is
It's
where
gonna
these
follow the
electrons are
same
going to be
pattern.
found.
So,
So
all you gotta
let's say
keep
that
in
we
mind,
happen to
really,
have
is
them,
that
they
the
don't
one
really
that is
move much from the
different
center.
is
So they're
atomic
in this little
radius,
range here.
simply because
And we're
bigger
going to
atomic
say that the
radius,
difference
less
between
energy is
the
required to
strength
use that
of these two
electron.
elements is 0.4. Now, if you're asking me, what do I mean by
We're
the
talking
difference?
about
You can take a look
electronegativity, so
here
we're talking
in
about that kind
the
of
top
like
part
pull,
of the
attraction. We're thinking
periodic
about it
table,
as
and just look at your
a
key.
tug of
It might
war
be in a
between
different
two
spot depending on which
elements.
periodic table
We've
you
got
have.
a couple of different
But that
things
top
we
part
can
tells
have
us
happen.
how strong each element
So,
is. So if there is
if we happen to have a
0.4
really big
difference in
atomic
between the
radius,
strength of these
and
elements,
we're
we're going to have
low
something called
ionization energy
nonpolar.
and low electron
covalent.
affinity.
So
then
that
we're
means
also
that they're
going
going to be
have
sharing.
a
They're
low
covalent, so they're going to be sharing electrons.
electronegativity.
And they're
Which
nonpolar
means
because
that it's
no one
probably not
has
strong. It's
the
not
electrons
strong
close
to
enough to
actually be
them
able
for it
take
to really
electrons.
affect their charge.
So this is going to
We
give
can also
up
have a
electrons.
situation in which we
If
have
we're in
elements that are
other
able to
situation
move it a
where we
little bit
happen to
more,
have a
but they're
really
not
small
able to
atomic
move it
radius,
completely
and
away.
we have a big
And in this
ionization
situation,
energy, that means we're
we
going
would
to have
talk
big
about that as
electron
being
affinity. That
polar,
means that we
covalent.
happen to have that element has a lot of strength with its ability to be able to
So
pull
if we
electrons
happen to
away from
have,
others.
let's say
So
element
this one's going to
A
be
is
the
stronger
one
than
that takes
element B.
electrons.
And so the electrons end
However,
up over here
we
much
can also
closer
have
to
a
element
situation
A
where it's
than
not a
element
give
B.
and take.
Since
This happens,
these happen
so
to
this
exist
give and
between
take
the
happens when we
spaces,
have
and
one
this
that is
has the
clearly
electrons
stronger than
closer.
the other.
Even
However,
though they haven't
we
taken
might
them,
have some
this
that
one's
are
going to be
almost
slightly
equally
negative
matched,
because of the
or
presence
one
of
might be
those
stronger,
electrons.
but not strong
So we
enough to take
indicate
everything.
that
In
by
this
using this
situation,
little
the give and
slightly,
take,
a little
we're thinking about a
sigma,
bully who's
a
strong enough
sigma
to just come
sign,
and steal your
and we
lunch.
put it
In
negative
the
there
other
if it's the one
situations,
with the
we're talking about a
electrons.
friend.
Over
you
here,
split your
since
lunch equally,
element
maybe they
B
happen to
lost
eat,
the electrons, or they're
3/4 of your
further
lunch,
away
but
from
you
them,
still get to share it because you're still having that.
then this one's going to be
last
slightly positive. So it's
So when we're
not
talking
as
about
positive
electronegativity, there
or
is a
as
range
negative
here.
as if we actually had those electrons
And if we happen
completely
to
taken
have
away.
an element on
But
this
because
side,
it happens to be found more in one
and
area than the
element
other,
on this
then it
side,
kind of affects the charge, just slightly.
then what we have in the center.
Now, anything
is
beyond that
where these electrons
1.7
can be found.
is going to be
So let's
ionic.
say that we
This
happen to
means
have
that
them. They don't
the
really move
element
much from
was
the
strong
center,
enough
so
to
they're in this
completely
little range
take
here.
away
And we're going
those
to say
electrons,
that
and
the
now they
difference
only took
between
themselves. So
the
one of them
strength
lost,
of these
one of
two
them
elements
gained it.
is 0.
And so anything
Now, if
over
you're
a
asking
difference
me,
of
what do I mean by the
1.7
difference?
is going to
You
give
can
you
take a
an
look
ionic
here
compound.
in the
This
top
is a
part
much
of the
deeper understanding understanding
periodic
about
table,
how it is that
and
we
just
get
look
these
at your
different
key.
compounds
It might be in
to.
a different spot depending on
form.
which periodic table you
So
have.
in the end,
But
just
that
to
top chart
summarize,
tells us how strong each element
everything with
is. So if
reactivity
there's
is going to come down to this idea of
0.4 difference
attraction.
in between the strength of these
And we want to make sure we
elements,
use those
we're
terms:
gonna have
nuclear
something
charge
called
and shielding.
non-polar.
Now, how attractive something's going to be is
So
going to
that means
depend
that they're going
on
to be
the
sharing
number of shells it has,
covalent, so
first
they're
and
going to be sharing
foremost.
electrons,
And
They're
then,
nonpolar
if
because
those are
no one
equal,
has,
the number of
the
protons.
electrons close enough to them for it to really.
These ideas of attraction are going to determine
We could
how
also
much
have a
energy we need to
situation
remove an
in which
electron,
we
or how much energy we need
have
in order to
elements that
have
are able to
something take
move
an
it a little
electron.
bit more, but they're not
And
able
anything
to
that
move
is
it
metal is
completely
going
away.
to be much
And
more
in
likely
this
to
situation,
give up its
we're
electrons
talking
because
about
it doesn't
that as
have as much of a
being
hold on them.
polar covalent.
Electronegativity is the overall, the average of these two concepts,
So
and it
if we
talks about
happen to
how
have,
strong
let's
something
say
is to be
element
able to pull that
A is
electron.
stronger than element
And so
B.
if they're about the
And
same
so the
strength, they're going to be
electrons end
nonpolar
up
and not have a
over here,
charge.
much closer to
If
element
there's a
A
little
than
bit of a
element B.
difference in strength, but not strong
Since
enough to be able to take
these happen to
electrons,
exist in two
then
different
they're going to be
spaces,
polar
and this has
covalent.
the electrons
And if we have
closer,
one that clearly
even
is
though they
strong
haven't
enough to be
taken
able to
them,
take
this
the
one's going to be
electrons,
slightly
then one's going to
negative
be
because of the presence
ionic,
of those
they're going to be
electrons.
ionic, and
So
one's
we
going to be
indicate
negative,
that
and
by
one's going to be
using this
positive.
little sigma
Hopefully
sign,
that helps
and
go
we put
through some of the
negative
big
there
concepts
just the one
behind
with the
periodic trends,
electrons.
and just let
Over
me know
here,
if you've got
since
any questions.
element B lost the electrons, or they're further away from them, then this one's going to be slightly positive. So it's not as positive or as negative as if we actually had those electrons completely taken away, but because it happens to be found more in one area than the other, then it kind of affects the charge, just slightly though. Now anything beyond that 1.7 is going to be ionic. This means that the element was strong enough to completely take away those electrons, and now they own them for themselves. So one of them lost, one of them gained it. And so anything over a difference of 1.7 is going to give you an ionic compound. This is a much deeper understanding about how it is that we get these different compounds to form. So in the end, just to summarize, everything with reactivity is going to come down to this idea of attraction. And we want to make sure we use those terms, nuclear charge and shielding. Now, how attractive something's going to be is going to depend on the number of shells it has, first and foremost. And then, if those are equal, the number of protons. These ideas of attraction are going to determine how much energy we need to remove an electron, or how much energy we need in order to have something take an electron. And anything that is metal is going to be much more likely to give up its electrons because it doesn't have as much of a hold on them. Electronegativity is the overall, the average of these two concepts, and it talks about how strong something is to be able to pull that electron. And so if they're about the same strength, they're going to be nonpolar and not have a charge. If there's a little bit of a difference in strength, but not strong enough to be able to take electrons, then they're going to be polar covalent. And if we have one that clearly is strong enough to be able to take the electrons, then one's going to be ionic, they're going to be ionic, and one's going to be negative, and one's going to be positive. Hopefully that helps go through some of the big concepts behind periodic trends, and just let me know if you've got any questions.